So today's means topic of discussion of this part is that in my last lecture I raised one question or raised my concern regarding the system. Now here a system. Let me paraphrase my question that what are the prerequisites a system must satisfy to so it allows us to draw the phasor diagram of that very system. Now here, as you know that I cannot means I am not quite acquainted with the use of this pen tablet, so I have drawn this one. Let me try to explain you what is a linear system, or more precisely as our phasor, while we are considering phasor diagram, our main interest is to understand how a system behaves with a sinusoidal input, right? So when we are considering only sinusoidal input, then it is pointless to consider system with any generic input. Here we will consider everything in terms of sinusoidal input, right? Now here in sinusoidal input, here you can see this y is equal to this line is like, you can write it like y is equal to mx. Here I have considered m is equal to 1. Here I have considered m is equal to 1. Now this okay, so what I was trying to tell you that when we pass, like, what is a physical example of y is equal to mx? The physical example of y is equal to mx is just like there is a sinusoidal voltage waveform, sinusoidal voltage source, and you have taken two perfectly conducting wire and you have connected them with your sinusoidal voltage source, and one end of those conductor pair you have connected with the voltage source, and you have the other end, and across the other end you are measuring the voltage waveform. Then what type of voltage you will get there? You will get something like whatever is given to the, if I consider like what I am trying to say, let me draw, then it will make more sense. Like here you have one voltage source and you take long wire, rather a pair of wires, and you just connect here. This is a voltage source and you just connect 1 voltmeter across here. So this one, this long wire, we can consider this as my system. Suppose these two wires are kept inside a black box and we consider them as a system. Fine. If it is a system, then you have to think that what type of equipment equation you can use to represent such system. The representation of this system, here I have marked by this dashed line, is like y is equal to x. Fine. Now, here what would happen if we replace this y is equal to x by something. Y is equal to x is an example of a linear system, or any system that is governed by y is equal to mx equation is an example of linear system. You can have infinite number of m, and you can have an infinitely large countable family of your set of linear system. That's a different issue. But whenever we are talking about linear system, a linear system must be governed by the equation y is equal to mx. Now, when we are talking about electrical system, obviously electrical system generally comprises of three different elements. What are those elements? They are resistor, inductor and capacitor, right? So this, now you have to think that how to claim a given resistor is a linear one. The answer is, you have to check its characteristics in VI plane. Now in this VI plane, if it behaves like a straight line, then it is an example of linear resistor. So for resistor, it is VI plane. What about inductor? For inductor, you have to replace this VI plane by I psi plane. So what is I and psi plane? I psi plane is that this psi indicates our self-flux linkage of a given inductor, and this I is the current that is flowing through that very inductor. So this inductor we must study its characteristics in I psi plane. Now what about capacitor? For capacitors, you have to change this plane by, it will become VQ plane, or in other way, sorry, not VQ, rather you should write QV plane. Why this is QV, not VQ, because the capacitor uh, the capacitor we consider charge as the independent variable and voltage drop across capacitor is the dependent variable. The amount of charge stored inside a capacitor at any given time is its independent variable, and voltage drop that we are going to observe across that capacitor is a dependent variable. So this is should be QV. So for capacitor it is QV plane. Now, now let me clear the canvas. Yes. Here, now let us take some example of a nonlinear equation or nonlinear system. So, I would like to share an image. Let me see whether I can locate it or not. Yes. So here, this is an example of a system having saturation. So it is a system with saturation. So this saturation, what is the problem with this saturation? A system with saturation, here you are giving a sinusoidal input, but you are getting a periodic output, but that output is no more a sinusoid. You are giving a periodic input, you are getting a periodic output, but what is the difference with our previous examples? And here you are giving a periodic sinusoidal input to your system, but you are getting a periodic non-sinusoidal output from your system. So, in order to visualize this, let me give you one example. Let me give you one example. Say you have a linear inductor. So while you are talking about a linear inductor, your linear inductor equation will be psi is equal to Li, or for instantaneous value you can write psi is equal to Li. Now this psi is equal to Li, this one, this is an example. what does this imply? This implies irrespective of the magnitude of your input current, your flux linkage is a linear function, or flux linkage will vary proportionately with your current. So, what could be an example of a linear inductor? Suppose you take a, an air core coil. Now that air core coil will never face saturation issue, and you can increase the current through that coil to any extent, and although the coil will have a very small value of L, but you will always see that let me try to give you a pictorial representation. Like you may have a very curve with very poor slope. This slope in psi I plane or I psi plane, it gives us the inductor. So for an iron core, you may have something like this. So for a small value of current, you will have a very high value of flux. But for an air core that is shown in yellow line, your inductor will never face any kind of saturation issue. However, what we can observe for this psi I, like if we take an iron core inductor, then obviously after certain time, if we linearly increasing our current from 0 to some value, then if the current level exceeds a certain value, what we will observe that our flux also gets saturated. Beyond that particular value of current, if we forcibly allow more current through the coil will not be able to produce more flux. So that is known as the saturation problem. So saturation problem, what was its pictorial representation? We just here you can see you are giving sorry, it is somewhat misplaced. Let me try. Yes, fine. So see here, it is you are giving a sinusoid, but you are getting a periodic but non-sinusoidal waveform. So what is the point? Suppose if you take a inductor that is having saturation issue, that is not linear inductor, in that case you can't plot Phasor diagram of that inductor. Like you can plot the Phasor diagram of your input current, because input current is a perfect sine wave. But what about the output flux? Output, if we consider inductor as a system with current as its input and flux as its output, then we will not, after our current exceeds its saturating limit or a particular value, we will not see any tangible change in our flux level. So that is very interesting thing to note, that for linear system you can only draw phasor diagram. So after you, means I do not know how many of you are still means continuing with me or means listening to this boring lecture. Now one that what we could figure out, a system must be linear. Now, do you think that only linearity will serve our purpose? The answer is no. Linearity is a necessary condition for drawing phasor diagram, but not the sufficient one. Then what is the another condition, or what are the other conditions we should consider? Now let us consider one RL circuit. Now you must have some idea about drawing phasor diagram of RL circuit. Here we are giving voltage to this RL circuit. Let us assume this R and L, both of them are linear. Now if this R and L, they are linear, then we can draw phasor diagram for that circuit. Suppose, however, let us consider that this RL, they are only linear, but they are not time invariant. If they are not time invariant, then what would happen? Suppose the value of R, at certain instance the value of R is 5 ohm, and the inductive reactance value is J 5 ohm. You got this circuit. At one instance of observation, you are having this 5 ohm and 5 ohm. So if you try to draw its phasor diagram, you will get V, and you will have I, where the magnitude of I will be calculated using formula V by root under 5 square plus 5 square, and your phase angle, this angle, what would be the value of this angle? It will be tan inverse 5 by 5 is equal to 1. Now this makes sense, but if this is a time varying circuit, after certain instance somebody come and observe that instead of 5 ohm it has become say 15 ohm and this one become 25. Then what are the problems we will be facing with this time varying circuit? So here it will become 15 square plus 25 square. So you will have a dilemma regarding magnitude of the phasor I, because magnitude of phasor I is continuously varying. If you allow your circuit parameters to vary, then obviously circuit quantity, that is current, will also vary. And accordingly, if your means R and L, if they are varying, both of them are varying at a constant proportion, like if you have 15 ohm, previously it was 5 ohm and your inductive resistance was 5 ohm, and in your next observation you found both of them have become 15 ohm, then that is okay, that is good. You will never realize a change in your phase angle as long as both of them are changing at a constant rate. But when there is a disparity, like here, our resistance value has changed from 5 ohm to 15 ohm and inductor value has changed from 5 ohm to 25 ohm. Now see the angle, what would be the value of this angle will be, it will become tan inverse 25 by 15, and here you will get some complicated value, not 1. So here your this angle will become something more than 45 degree. So in a nutshell, your whole phasor will become meaningless if you have drawn it for a time varying system, right? Another thing, so what we can conclude, the two important point, that is a system must be an LTI system in order to draw its phasor diagram. Until unless a system is an LTI system, we can't draw its phasor diagram, right? Now, in my next video, I will discuss that even if a system is an LTI system, you can't draw its phasor diagram just after you means connecting that system with supply. You can't draw its phasor diagram. Okay, no need to lengthen this discussion. Just let me give you one simple example. I hope you heard about transient and steady state. This transient and steady state, what is transient condition? If you can recall the KVL equation for a given RL circuit, it was like L di dt plus Ri is equal to V. Now this V being your input voltage, if you excite the system with sinusoidal voltage, it will become Vm sin omega t. Now with this Vm sin omega t, if you excite your system, at first what you will observe, I am not solving this differential equation, that will what we can understand that in our current expression there will be some initial transient and then there will be a steady state. This steady state, what is that steady state? This steady state condition, value of current is what you always write, that is Vm by root under omega L square plus R square. This with sin omega t minus arc tan or tan inverse omega L by R. So this expression is the expression of current in steady state condition. My handwriting is not good. Let me write it once again. It is Vm root under omega L whole square plus R square, and here it is sin omega t minus tan inverse omega L by R. Now, instead of finding out a mathematical expression for the transient, because transient is not required right now, let us try to understand this concept intuitively. Why or how this transient comes in the picture. See, when we are talking about an RL circuit, in RL circuit, what are the components you have? You have one R. Sorry, I have drawn an L. You have one R and one L. Now, R is like, I hope, although nowadays everyone is using LED bulb or crystal bulb, but you have, at least in your laboratory, you have encountered with tungsten filament lamp bulb. That tungsten filament lamp bulb is a perfect example of R resistor. Actually, it is if you are looking for a pure resistance, then tungsten bulb is the most means is one of the very close example or very near perfect example of a pure resistance. Now what happens when you connect a bulb with your voltage source? At the very beginning or just after connecting the bulb, you get full lumen output from that bulb, full light energy from that bulb. But on the contrary, if you are think about your fan, once you put on the switch, it takes some time to reach its final speed or steady state speed. So, in short, what I am trying to say that a fan is it contains an inductor of very high value, and any inductive circuit doesn't, the property of inductive circuit is that, later on we will discuss more on this because our life is only filled up with resistor, inductor, all these things. So the property of an ideal inductor is to oppose any rate of change of flux linkage. What I am trying to say that suppose this inductor, this is linked with a self flux linkage of psi. Now if we try to change this psi value, how can you change psi value? You have to change the current that is flowing through this inductor I. So this inductor, what it will try to do, it will try to oppose that flow of current. And how it can do so? It will, okay, not going to much physics, that the inductor must oppose the rate of change of flux, and this rate of change of flux, so inductor must oppose the very cause of current or very cause that is responsible for rate of change of flux. Mathematically speaking, inductor has a great concern for this d psi dt. And you must have noticed that in case of linear time invariant inductor, we write the voltage induced across an inductor is L di dt. This whole idea of L di dt comes from this basic property of inductor, that it always tries to oppose any rate of change of flux linkage, and while doing so it opposes any instantaneous change in its current value. So when you connect these two in series, you connect R and you connect L in series, then what will happen? The inductor will, although the resistance is quite okay, is like a monk or a yogi who is totally okay with anything, means whatever you will offer to him, he will be happy with that. But the inductor is not like that. Inductor will try to oppose the change of current, and that is why in case you are applying a sine wave, there will be some initial transient, and then you will get the full sinusoidal waveform. So here, although this is not a very clear diagram, but here you can see that this bold line, it indicates our resultant current component, and this one, the monotonically decreasing line, it represents transient component, and this dashed line, it represents steady state component. So what is the essence of showing you all this? Because unless your transient component completely die down, because you can see your total, your result means your resultant current is a combination of your transient and steady state. Do remember, steady state is only sinusoidal in nature, while the nature of transient is monotonically decreasing, and it is either monotonically decreasing or monotonically increasing. That's a different thing, but generally you will get a monotonically decreasing current. So in that case, if it is monotonically decreasing, then you have to wait till that time point, or till the time your transient completely die down. Until unless your transient dies down, you will never have a pure sine wave across your output terminal. So in a nutshell, how long should we wait? The answer is that we should wait till the transient dies down, and the waiting time is known as reaching the steady state condition. Once your system reach steady state condition, then you can assume that there is no more transient. So let me delete this one. Sorry. An LTI system and the obvious question is that when will we reach steady state? The answer is that we have to wait for 4 times of the time constant of that very system. For each and every dynamic system, dynamic system means system with either inductor or capacitor. Detailed discussion on dynamic system is not under the purview of the present course. For dynamic system, your 4 into time constant, if you allow your system this much time, then the system will reach your steady state condition. For most of the practically available system, it is advisable that you wait for at least 5 minutes, and then whatever means variable or quantity you will observe by your measuring instrument, you can safely go for phasor diagram. Have to wait for 4 to 5 minutes. For most of the practical system, it is 4 to 5 minutes. And there is no harm if you can wait for some more time, but don't wait so long that means suppose you visit a factory, you are very excited to draw a phasor diagram of a given means of a machine, and you are waiting for its steady state, and suddenly you means notice that the means production or whoever is there, the production staff is about to shut down the machine because you have been waiting for so long, for hours, that they have to stop the machine. So don't behave rationally, and it is safe if you can wait for 5 minutes. You can draw phasor diagram of any system. In my next class, I'll discuss locus diagram. What is locus diagram? You can expect some question from phasor diagram as well as from locus diagram.